All right, so today the plan is to cover transformations in three-phase circuits. So let me pull up a thing here. Actually, I'm gonna make sure I save this. Why aren't you finding my thing? That should be enough for now. All right, let's see. So the last thing that we talked about was our single phase equivalent circuit models for a three-phase circuit. Entirely off of a YY system. And the circuit analysis in our single phase equivalent circuit was rather trivial to do because it's just making a big ugly three-phase circuit look like a single loop circuit, which we should be able to tackle pretty easily at this point in our circuit analysis careers. So what we're going to do now is we are going to figure out how to transform a delta connected source into a Y connected source and a delta connected load into a Y connected load so that we can make any three-phase circuit configuration. We can analyze it as if it were a YY source and then use transforms to go back if we need information that can't be provided by a single-phase equivalent circuit. So let's begin. So the first bit we're going to talk about is transformation of balanced sources. And we kind of went over this a little bit at the end of Tuesday's lecture when we figured out how to get our line voltages. But if we have a Y connected source, where VAN is some magnitude or phase voltage, that's what VP is going to stand in for, angle 0 degrees. VBN is VP angle minus 120 degrees. So we're assuming a positive phase sequence, and VCN is equal to VP angle minus 240 degrees. We can determine what our line voltages are as follows. So in this case, we're going to focus on the line voltage VAB, which would be the voltage measured between the terminals A and terminal B of our three-phase Y source. If we use Kirchhoff's voltage law, we can effectively have just a little loop in this triangle. So this would be a KVL loop. And we can see that VAB is simply equal to VAN minus VBN. Since we know that VBN is simply VAN shifted by negative 120 degrees, this becomes VAN times 1 angle 0 degrees minus VAN times 1 angle minus 120 degrees, or VAN times 1 angle 0 minus 1 angle negative 120 degrees, which is VAN times square root of 3 angle 30 degrees. And similarly, we could find then that BC is VBN times square root of 3 angle 30 degrees, and VCA is VCN square root of 3 angle 30 degrees. So we can use these relationships to develop a transform. So if we have a Y-connected source, C, we want to transform to a delta connected source. VAB, VBC, and VCA. All we do is we multiply our phase voltage. So I'm going to do VP angle, multiply it by square root of 3, 30 degrees. So that's us converting to from Y to delta. If we wanted to go the opposite direction, shouldn't be too difficult to see that we could simply take our phase voltages from our from our delta connected source, and we would simply multiply by 1 over the square root of 3 angle negative 30 degrees. So to go from Y to delta, we multiply by root 3 over 30 degrees, and to go from delta to Y, we effectively divide by root 3 over 30 degrees, or root 3 angle 30 degrees, which is the same as multiplying by 1 over square root of 3 angle negative 30. So this allows us to easily transform back and forth between a Y connected source to a delta connected source and vice versa. Hopefully the math here was pretty straightforward. So any questions about this before we move on to load transformations? Let me turn off the ringer on my phone. All righty. Another page. All right, so let's say that we have a Y connected source, excuse me, a Y connected load. Actually, I'm going to use the other way to draw this because it'll just make me happier. So we have a Y connected load and a delta connected load. Z delta A, Z delta B, and Z delta C. Here's A, B, and C. So if we look at the impedance seen between the A and B terminals of the Y connected load, we get Z, sorry, it looks too much like a delta. AB is equal to ZYA plus ZYB. Right up here. And if we look at the impedance between the terminals A and B of the delta connected load, we would see Z delta A in parallel with Z delta B plus Z delta C. So Z delta A is in parallel with the series connection of the other two impedances. So we'd have Z delta A multiplied by Z delta B plus Z delta C over Z delta A plus Z delta B plus Z delta C. Hopefully this looks a little bit familiar, although the terminology is different. What we are about to do is define the rules for a delta Y conversion in a three-phase system, which we talked about way at the beginning of class for one of the homework problems. And then when we got into impedances, I think I made you guys actually derive this, so we won't spend a whole heck of a lot of time on it. but just telling you guys what's up. We can do a similar thing, and we could find that ZBC would be ZYB plus ZYC is equal to Z delta B times Z delta A plus Z delta C over Z delta A plus Z delta B plus Z delta C. And lastly, we could see that ZCA is ZYC plus ZYA is equal to Z delta C, Z delta A plus Z delta B over Z delta A plus Z delta B plus Z delta C. So if we do a Y to delta transformation, we can see that Z delta A is simply ZYA ZYB plus ZYB ZYC plus ZYC ZYA divided by ZYA. Z delta B becomes that exact same numerator, ZYA ZYB plus ZYB ZYC plus ZYC ZYA over ZYB, and Z delta B, excuse me, C becomes ZYA ZYB plus ZYB ZYC plus ZYC ZYA all over ZY. Now, if our load is balanced, that means that ZYA, ZYB, and ZYC all have the exact same value. So in that case, these guys reduce significantly, right? So if ZYA and ZYB are the same value, we have ZY squared plus ZY squared plus ZY squared. So it's going to look like 3ZY squared over ZY is 3ZY. And we'll get the same result here and the same result here. So we can see that when we have a Y-connected load, ZY ZY Y A, B, C, our neutral connection. If we want to convert to a delta, we simply say that Z delta is equal to 3 ZY. So what do you think we should do? Sorry, let me finish this guy up here. A, B, and C. So what do you think we should do to convert from a delta to a Y?
It's just algebra. Oh,
Right.
Go back.
So if we know that Z delta is equal to 3ZY, it stands to reason that ZY is just equal to
Over 3.
delta over 3. Exactly right. We could go through and use the actual delta Y transformation relationships and all that kind of stuff and go through that math, setting all of the Z deltas equal, but we're going to get this simple result that we can get just algebraically manipulating our first relationship, just like we did for the sources. So to convert from Y to delta, we multiply the load impedance by 3. To convert from delta to Y, we divide the load impedance by 3. It's that easy. So with that in mind, we now have the means by which to convert any three-phase circuit into a YY circuit. So let's see. That's a YY, so we don't want to do that one. All right, so let's work an example problem. In a balanced three-phase delta Y system, and I'll write out this problem statement. In a balanced three-phase delta Y system, the source has a ABC phase sequence. The line and load impedances are 0.1 plus J 0.1 ohms and 10 plus J4 ohms respectively. If the line voltages at the source are VAB is equal to 208, angle 0 degrees, volts RMS. Calculate the line voltages at the load. All right, so we're going to look at this problem. And in your homeworks that I posted 3 homeworks this morning for all of the three-phase stuff. One has YY circuits, and I think it might have a Y delta. So effectively, the first homework set all has a Y source. The second homework set, I think, all has a delta source. And then the third homework set is about power, which we're going to cover on Monday. So in all of those homework assignments, though, I never give you a circuit to analyze. I just describe the circuit just like I've done here. So the first thing that I would typically do, at least until I get comfortable with analyzing three-phase circuits, is draw a circuit diagram that's representative of the problem statement. So in this case, we know that we have a delta connected source. So let's start by drawing that guy. Minus plus. This is VAB. This will be VBC. C, like so. So this is the basic configuration for a delta source. Then we are going to have our transmission lines. So let's call this ZW for Z wire. Here's our B phase transmission line. Here is our C phase transmission line. Oh, but it should still be W because they're all equal. Capital A, capital B, capital C. And finally, we have our Y connected load. And here is our load neutral. So this is the information, sorry, this is what the circuit looks like. Then I would consolidate the information that I know. So I know that the voltage VAB is 208 angle 0 degrees volts RMS. I know that ZW is 0.1 plus J 0.1. And I know that ZY is 10 plus J4. I'm asked to calculate the line voltages at the load, so I will make a note of what I'm looking for. So specifically, I need this guy VAB, and then once I know it, I can get all the other line voltages just as easily. So the only one I'm actually going to bother drawing out there is VAB. So in order for us to use our single phase equivalent circuit, we're going to have to transform our delta source to a Y source. In my opinion, we don't actually need to redraw anything here. It should be pretty intuitively obvious. Well, maybe for this first time, I should redraw it. So let's start with how we're going to convert that delta connected source to a Y connected source. We know that VAB, using our transformation, we know that VAN is simply going to be VAB divided by √3 angle 30 degrees, which is the same as multiplying by 1 over square root of 3 angle negative 30 degrees, like I showed you earlier. And so from this, we have 208 angle 0 degrees volts RMS divided by √3 angle 30 degrees gives us 120.089 angle negative 30 degrees volts RMS. So now that I know what VAN is, I know what VBN is and VCN as well, just because I could shift this by 120 and 240 degrees respectively. So I could redraw my circuit. Again, I don't feel that this is going to be necessary probably beyond this example problem, to be entirely honest. So here's VAN. Here's VBN. Here's my neutral. CN, A, B, C, and the rest of my circuit is going to look exactly the same, which is why I don't think it's super necessary to redraw things. And again, what we are looking for is so now that we have a Y circuit, we can redraw the single phase equivalent circuit. And I'm going to be dealing with the one just for the A phase. So my A phase equivalent circuit looks like this. I've done a little bit of rounding there. I'm just calling it 120 angle negative 30 degrees. And this voltage is VAN. And this voltage that I've drawn, VAN, is the phase voltage at the load, which is not the line voltage at the load, but it is necessary to determine the line voltage at the load, because once we know VAN, we can simply do what's effectively a delta Y transformation on that voltage, right? Just like we did earlier. So we know that if the line to neutral voltage has a value, getting the line to line voltage is simply multiplying by square root of 3 angle 30 degrees, because that is exactly what the transformation that we first dealt with, converting from Y to delta, allows us to do. So how could we go about solving for VAN?
Voltage division.
Yeah, voltage division seems easy enough. So that means that we'd have 120.089 angle negative 30 degrees volts times, let's see, I'm going to have 0.1 plus J 0.1 ohms here, plus 10 plus J4 ohms here. Oh, and this is 10 plus J4. 10 plus J4 ohms here. And this gives me 118.655 angle negative 30.293 degrees volts RMS. So voltage division. Analyzing these single phase circuits should, again, pretty much be a joke to do, based on the amount of circuit analysis techniques that you guys have learned to this point. So our line voltage VAB is just VAN times root 3 angle 30 degrees. So if we do that operation, we'll get 205.517 angle negative 0.293 degrees volts RMS. VBC, we just shift that by negative 120 degrees. So 205.517 angle negative 120.293 degrees volts RMS. And lastly, VCA. Come on, pen thingy, do your job. There we go. 205.517 angle negative 240.293 degrees volts RMS. And we have solved this problem by using our transformations. So let me look at this next problem. And let me also look at your homework set. Yeah. All right, so this next problem that we're going to look at is actually homework problem 5 from set 17. It's one of the more difficult ones, so that's why we're going to talk about it. Let's see, I need to append. All right, so the problem statement says that we have a balanced three-phase system with a Y-connected source. So let's draw that real quick. With VAN is equal to 120 angle 20 degrees volts RMS. So we'll write that down in just a minute. And our load consists of two balanced impedances connected in parallel. A Y-connected load with a particular per phase impedance of 8 plus J2 ohms, and a delta connected load with a per phase impedance of 12 plus J3 ohms. So a question that I often got about this particular problem was, how the heck do you draw those two loads in parallel? And there's a couple of different ways that we can do it. So let's talk about them. So we have a delta connected load and a Y connected load, and they're in parallel. One question I've also been asked for is it possible to connect three-phase loads in series? And the answer is no. You could connect different portions of each phase in series, but whenever you have multiple loads in a three-phase system, it's assumed they're all connected in parallel between the terminals of the transmission lines. Okay. So up here, we have our A, effectively like a bus, and down at the bottom, we have a B bus, excuse me, a C bus. So for instance, we know that there is going to be a delta connection between A and B, one portion of the delta load between B and C for sure. Now what I'm going to do is I'm going to put my neutral point for my Y-connected load here. And so I have my Y-connected load is between A in neutral, B in neutral, and C in neutral. And then lastly, this is my delta portion of the load that's between C and A. So I guess my first question is, does everybody understand why the two parallel loads look, I don't know, in this odd configuration? Everything is set up properly, but alternatively, we could do, and I'll just do the load side here. So here's C, excuse me, A. B and C. So I could do something like this. This is Z delta, Z delta, Z delta. Y align, Y is neutral. I prefer the way up top just because it literally takes up significantly less space, but this is perfectly acceptable. And you could transpose the position of the delta and Y in this one if you so chose. And at the end of the day, how we draw them is really not going to remotely matter. All right, so getting back to the problem at hand. We are told that our voltage VAN is equal to 120 angle 20 degrees volts RMS. We are told that ZY is equal to 8 plus J2. We're told that Z delta is equal to 12 plus J3. And we are told that Z wire is equal to 0.1 plus J 0.8. And what we want is the line currents and the phase current, dang it, through each load. So our line currents are going to be IAA, IBB, ICC. Our phase currents are going to be IAB, IBC, ICA. So that's for our delta. Our Y, it'll be that should be BN, IAN, and ICN. So we're looking to figure out just a whole bunch of currents in this system, okay? And it probably seems to you guys that it's going to be rather complicated. And honestly, largely it won't be. And so let me explain what I mean by that. So what, if any, transformations am I going to have to do to analyze this problem to set it up where it looks like a Y circuit? So what's the only part of this circuit that isn't connected as a Y? Let's start there.
You just transform the delta load.
That's it, yeah. So I'm gonna come up with a new load that's gonna be called Z delta Y, and it's gonna be Z delta divided by 3. So that's gonna be 12 divided by 3 is 4 plus J1 ohms. And now I can draw my single phase equivalent circuit. So if we come down here, let's look at the A phase. We have 120 angle, was it positive 20 degrees? Yeah. Volts RMS. Here's our neutral. Here's our wire, ZW, which had an impedance of 0.1 plus J 0.08 ohms. Here's the A terminal. We have ZY, which is 8 plus J2. And in parallel with that, we have the delta Y, which was 4 plus J1 ohms. So, let's see here. So from this guy, we can determine all of our line currents. We can also determine all of our phase currents through the Y connected load, but we can't determine all of our phase currents through the delta connected load because we've transformed it. Does that make sense? So because we've done a transformation on it, it has fundamentally different relationships now. But we can determine these two pieces of information pretty easily and then use them to figure out what the phase current is going to be. And there's a couple of different ways that we can approach determining the phase current. So if we have time, I'll go over at least 2 of them. So before we get ahead to that though, let's determine what we, let's calculate what we can determine directly. So which of these 2 quantities do you want to find first? The line current or the phase current through the Y load?
The line current.
Okay, I personally feel that that's the easier one to calculate as well. So how I would find the line current, say that IAA is equal to our voltage drop divided by the total series impedance that our voltage source sees, which in this case would be Z wire plus ZY and Z delta Y in parallel. I can make this smaller so I don't use up so much room. So if we put numbers into this guy, we're going to have 0.1 plus J 0.08 ohms plus 8 plus J2 times 4 plus J1 over 12 plus J3. And BAN is 120 angle 20 degrees volts RMS. And if we do this math, we get 41.875 with an angle of 4.897 degrees amps RMS. So determining the line current, in my opinion, fairly easy. How could we use this information to determine the phase current through the Y-connected load?
Current division.
Yep, absolutely right. So IAN is equal to IAA multiplied by, let's see, I'll use the reciprocal version because I'm not sure if you guys know the other one. So we want the current through that one. So it's going to be 1 over 8 plus J2 ohms, 1 over 4 plus J1 ohms. And over here, it'll be 1 over 8 plus J2 ohms. And using that current division, I get 13.958 angle 4.897 degrees amps RMS. So now that we know those two guys, how could we determine this current IAB? So what I would suggest is that we perform Kirchhoff's current law at this node and develop a relationship. So for instance, we can see that IAA is flowing in and ICA is flowing in, right? So this guy here is going to flow into that node, and flowing out, we're going to have IAB and IAN. So let me bring this down to the bottom here. Let me add a new page. So I believe what I said was that we had IAA plus ICA was equal to IAB plus IAN. Is that correct?
Yes.
All right. So I'm just going to do some algebraic rearrangement here. We know what IAA is, so I'm going to put this on this side. I'm going to subtract IAN because we know what that guy is, and this is going to be equal to IAB minus ICA. So if I've done my little basic algebraic movement here, everything should be groovy. Now, I know that IAB, or excuse me, I know that IAC, or dang it, ICA is going to have the exact same magnitude as IAB because this is a balanced system. So this is really IAB minus IAB, 1 angle negative 240 degrees, right? Because ICA is the exact same thing as IAB, but shifted by negative 240 degrees. So that leaves me with IAB, 1 angle 0 minus 1 angle minus 240 degrees. And I think that is square root of 3 angle negative 30 degrees. And now I can calculate IAB. $16.118 angle 34.897 degrees amps RMS. So this method, we simply use Kirchhoff's current law and the original circuit diagram to develop a relationship that would allow us to calculate for this phase current through our delta connected load. And from this guy, we could shift by negative 120 to get IBC and shift by negative 240 to get ICA, and nothing wild there. Now let's talk about, since I have 10-ish minutes, the other way that we could do this, which to you guys actually might seem a little bit easier. So let's revisit our single phase diagram here. If I know this voltage VAN, which I can figure out based on the information that we already have, I could transform that to the line, so that would be a phase voltage VAN at the load, right? Because it's over it's the voltage drop over one phase of the Y connected load. Well, I could transform that to a line voltage, which would be the same as the phase voltage over the A phase of the delta connected load. Does that make sense?
Yes.
So yeah, so what I'm saying is, let's see here. If I can get this voltage and transform it, I will get this voltage. And if I know that voltage and divide by the impedance, I will get the phase current through the delta connected load. So let's verify that real quick. So VAN is going to be IAN times ZY, which is going to give me 115.104 angle 18.933 degrees volts RMS, which means VAB is VAN times √3 angle 30 degrees is 199.366 angle 48.933 degrees volts RMS. And now using Ohm's law, IAB is VAB divided by Z delta is 16.118 angle 34.897 degrees amps RMS. So we get the same result either way. So once you understand the relationships in a balanced three-phase circuit, It really starts to become as easy as any other circuit, and you can just use whatever analysis techniques you're comfortable with. So you don't have to go through and be like, oh, so I have to go and use KCL and do this, that, and the other. You can use voltage transformations to get the exact same information. It's all about understanding the relationships between a line to neutral voltage and a line to line voltage, or, you know, understanding. So that was the key to doing it this way. Here, the key to getting an answer was understanding that the phase currents through the delta connected load have to have equal magnitude, but are shifted by a very specific amount in phase. And so doing that, you know, it looks like we have two unknowns here, but we really only have one unknown, since we know that it's a balanced system, because we can develop a relationship between the two unknowns that allows us to simplify. So once those types of relationships start clicking and making sense, all of this three-phase circuit analysis becomes extraordinarily trivial. It just takes practice to get those relationships to be ingrained in your mind. I would hope that you guys will have some time over this weekend to look at some of the homework problems and all that kind of good stuff. And we can spend some time next week answering them and trying to reinforce those relationships. What I have planned for the remainder of the class, so this is all I have about just simple three-phase circuit analysis, is that we're going to talk about power in three-phase circuits, which is just going to be using the exact same power relationships that we developed for single-phase circuits. So we're going to have, you know, complex power, apparent power, average power, and reactive power. And they're all going to be based on the exact same things. Complex power S is the RMS voltage times the complex conjugate of the RMS current. Except that now there are three phases, so we'll multiply by 3. It's really that simple. We'll go through things and formalize it, but it is that simple. Then we'll talk about power factor correction in a three-phase system, which is the exact same thing as power factor correction in a single-phase system, except that you have to divide by 3 because now you're putting in 3 capacitors. And then after that, I have planned that we'll talk briefly about unbalanced three-phase systems. I say that I have that planned because I've never once been able to actually teach that lecture in any of the 7 times I've taught Circuits 3 now. So if we get to it, great. If not, that's perfectly okay as well. I would rather spend more time making sure that you guys understand this, so that when you get into your senior level classes, should you choose to take the class on electric machinery and power and all that kind of stuff, that Dr. Batari and or Dr. Cox doesn't have to spend a whole hell of a lot of time reteaching you all of this or re-explaining it, and just blazing forward to get something that I feel like maybe we should teach out. But yeah, no one else has ever taught unbalanced three-phase circuits in Circuits 2. I just felt like doing it. So anyway, so all of that is to say then that if you guys feel like you want and need more time to understand the fundamentals of this stuff, I'm happy to give it to you, and I'm happy to continue to explain stuff, work example problems and all that kind of stuff, so that we can cement these relationships now instead of you struggling in later classes. All right, that's enough out of me. So I will catch you guys on Monday unless there are any further questions.
I had a question about the exam.
Yes.
So on the syllabus, you had it scheduled for the last Monday, like when you assign it for the last Monday. Um, but the last day of class is Thursday. Are we just not gonna have as much time to do it, or does it not matter because of when grades are due?
That's the deal there. It does not matter because when grades are due. So your grades
Okay.
are due later on the following week. So I understand that the quarter ends on that Thursday, and if you feel that you need to get the test in before the quarter ends, that's on you. If you want the full week to do it, I will give it to you.
All right.
So
I
does
just
that?
wasn't sure when grades were due.
Yeah, grades are due. I think Tuesday or Wednesday of the week after classes end.
Okay.
I'll double check on that just to make sure. If that isn't the case, but I think I looked at that, then I will simply, I'll either we'll definitively drop the that last lecture on unbalanced three-phase systems, and I'll move the exam up to Thursday, which would mean that you could turn it in the following Thursday and everything would be groovy. Um, as as far as the logistics would work.
Okay.
So
Thank you.
Yep, no problem. But I would rather give you guys more time to work on it. I don't think it's hard. It's like the other tests. It's the homework problems, but instead of a set on specific things, it's like a homework set over everything we've covered since the last test. So anyway, usually I can work out you guys' tests that I'm giving you a week to do in roughly an hour. I'm a jackass with a PhD. So, and also it's pretty easy for me to answer the questions because I'm the one that posed them. But anywho, any other questions?
No, sir.
All right, cool deal. Well, I will catch you guys on Monday morning.
Have a good weekend.
You too.